Hi everybody, in my previous couple of videos we went over a chi-squared analysis. In that particular example we had only two levels to a single variable. Now I'm going to complicate that just a little bit more by still using one variable, but this is going to have 5 possible values that the variable could be. And what we're also going to do is assume that the variables should appear with equal probabilities or equal frequencies among all of those 5 values. I'll walk you through the scenario in a moment. And so as you can see, it's a little bit more complicated than our 2-cell chi-squared analysis. This one's called a 5-cell chi-squared analysis, specifically with equal probabilities assumed. But let's walk through this. Okay, so once again, a chi-squared analysis uses only categorical variables. And in this case, we're using only a single variable. You can have chi-squared analyses with 2 variables, 3 variables, and so on. We're just going to walk through the single variable chi-squared in this video, and then in the future, we'll do a few other kinds, okay? Now, what we're trying to do is see, does the pattern I'm seeing this variable appear as, does it match what I assume it would be if my theory is true? So maybe my theory is these should all appear with equal probabilities or equal frequencies. Or maybe your theory is something else that maybe actually you don't expect them to appear with equal probabilities. We'll cover an example of that later. And so that's basically what we do, and we find out mathematically if your pattern is what you expect it to be, or if it is different from what you expect it to be, significantly different from what you expect it to be. So as I said, last time we covered a 1 variable chi-squared with 2 levels. In this case, we're going to cover one with 5 levels. So we're going to see how this goes. And we're starting with the assumption that they should appear with equal probabilities. That's often the case where if you have no reason to believe otherwise, you generally would start with that. Now, I'll cover some other examples in the future, though, of where you wouldn't expect them to actually be equal probabilities. So now let me walk you through our little scenario for our example. All right, let's imagine we've got this guy named Franz. Franz opens up a brand new hot dog stand. He's really excited to sell these hot dogs. And on his menu, he's got 5 different hot dog styles. It doesn't really matter what they are. Let's say one's Chicago style, one's New York style, or whatever, right? Something like that. And so he sets them up and he labels all of the hot dogs. He'll call them 1 through 5, we'll say, for his menu items. And now what he wants to do is he's going to see how people how people purchase these hot dogs. He wants to see, is one of the hot dogs being bought, more often than others, and are other hot dogs being bought so much less that maybe I shouldn't even offer them on the menu. He just wants to start gathering some data. I'll show you what he can do with that data once we've figured it out. So his default hypothesis, of course, is at this point he has no reason to believe that they're being purchased at different probabilities or at different frequencies. And so he starts off with the null hypothesis of, let's just assume that they're all being purchased at the same frequencies or probabilities. So his null hypothesis looks like this. Again, the probability of anybody purchasing the hot dog number 1 is the same as the probability of anybody purchasing hot dog 2, which is the same as the probability of anybody purchasing hot dog 3, and so on, right? So he assumes that they are all equal probabilities. Now, it's also possible that they are being purchased with different probabilities. Maybe people prefer hot dog number 3 or hot dog number 2 or something. Now, if that is true, what he's going to see is instead evidence that would support the alternative hypothesis. The alternative hypothesis could specify which one. However, we don't know, right? We don't know at this point. And so we just leave it open to, if there's anything wrong with this null hypothesis, then we will reject it, okay? And then assume that actually that's not true. In other words, one of the hot dogs is being purchased or is more likely to be purchased with every given interaction or interchange than is any other one. Or one's being purchased even less than some of the others as well. That could also be a possibility. So we're going to see how this works. So Franz spends an entire week and he writes down very carefully, keeps very good data on which hot dog style is being purchased. And this is what he sees. So in other words, he sold hot dog number 1 26 times over the course of that week. Hot dog number 2 was sold 31 times. Hot dog number 3 was 45 times, and so on. Okay. So now what he wants to do is see, is this a significantly different pattern than I would expect if they all had an equal chance of being purchased to one another? Okay. Now, as you can see, he observed a value for the hot dogs 133 times. In other words, he sold 133 total hot dogs in the first week. The reason I know that is because I added up all of these values to get 133. So that means the number of observations that we have of this variable is 133. Therefore, n equals 133. Now I need to know n before I can figure out the expected not the expected probabilities, but the expected frequencies of the hot dogs. This is a little bit counterintuitive perhaps, because what we do is we figure out what we should see if the null hypothesis is true after we've already seen the observed data, because we need to know how many observations of the variable we had. Now, sometimes you can set up ahead of time how many variables you're going to collect, or how many observations, I should say, of the variable that you're going to collect. But in many cases, we have to wait until we've just surpassed the time period and figure that out. Anyway, so we have 133 observations. So now I need to figure out what would I have expected to see in these categories. So if my null hypothesis is true, and I had sold 133 hot dogs, I expected them to be purchased with equal frequencies. Okay, so what that means is because there are 5 categories, I expected to find 20% of all hot dogs in any of all hot dog purchases of any style. In other words, 20% of my hot dog sales should have been hot dog number 1, 20% should have been hot dog number 2, and so on if my null hypothesis is true. Now, a way you could figure that out is just to take 100% and divide it by however many cells that you have, if it's a 1-cell chi-squared analysis, or I'm sorry, a 1-variable chi-squared analysis. And of course, 100% divided by 5 is 20%. Okay. So what that means is that if I multiply 133 hot dogs by 20%, that tells me how many of those hot dogs I should have expected to see in any given category. And in this case, that's 26.6 hot dogs. So I should have expected any given hot dog, I should have expected 26.6 of any given hot dog to have been purchased. Okay. Now, if you don't like that idea, if that's a little too confusing, that's correct, the way to do it. You could also just take 133, divide it by 5, and find out how many hot dogs should be in each category. And of course, you arrive at the same answer, which is 26.6 hot dogs. Now, some people get confused. They say, wait, 0.6 hot dogs? You can't have 0.6 hot dogs. Well, first of all, of course you can. But yes, that's a little bit weird to assume that you're selling a 6/10ths of a hot dog, right? That's fine though, because that is the expected probability. This is just the rules of math, the rules of probability saying this is our best expectation. That doesn't mean that that's what you observed, okay? It'd be a little weirder if you observed half a hot dog or something, but to expect half a hot dog, that's fine. Okay, so then if we put this all together, what I say is, here's what I saw, right? This is the actual hot dogs that I observed being sold, but this is what the laws of probability tell me I should have found if my null hypothesis were true, and they each had equal probabilities of being purchased, okay? So that's what we should have expected. Now our task is to mathematically compute and figure out whether this is significantly different from this, whether these frequencies I saw are significantly different from these frequencies. And here, of course, is how we do that. It's the exact same equation we used in the 2-cell chi-squared. We're just going to now expand it to include 5 cells, okay? So now let's walk through that on the next slide. Okay, so here's my same table, and I'm going to plug every value into the equation as like so. As you can see, I've got 5 instances of the equation because I have 5 cells. Okay, so I need to represent each cell. Now, some of you are going to go, wait a minute, don't you have 10 cells? And the answer is no, because I'm just interested in the observed frequencies of the cells to count as cells, right? This is just theoretical. The expected cell frequencies is just theoretical. It's my idea. And so they're not like real cells. I don't need to count them. I'm looking for the possibilities and the actual frequencies for each cell. And in this case, I have 5 cells because the hot dog could only be one of 5 values, right? Anyway, so I do this. So I have the observed cell frequency of 26 for cell 1, in other words, for hot dog 1. And the expected cell frequency for hot dog 1 was 26.6, so that goes right there. And then I divide by the expected cell frequencies after, of course, I've squared the difference. Then for cell 2 right here, 31 is my observed cell frequency, 26.6 is my expected cell frequency. And of course, in this case, because we had equal expected cell frequencies, it's always 26.6 in this portion, okay? The only difference is what I'm plugging in right here, the observed cell frequency. So for cell 3, for cell 4, and for cell 5 is 18. Anyway, now all we do is solve for chi-squared. So let's do that on the next slide. It's quite simple to do. All right, here's the same equation. Obviously, what we do is we first have to subtract before we can square, because we always start off with the parentheses first. So if we subtract every value, 26 minus 26.6 is, of course, negative 0.6. 31 minus 26.6 is, of course, 4.4, and so on. So we just subtract there. Now, a quick trick that I explained earlier, you can always pause at this point to check your math. What you can do is just ignore the squared value for a moment and just add these values across in the numerators. So for example, negative 0.6 plus 4.4 plus 18.4 plus negative 13 or minus 13.6 minus 8.6 is 0, and it should always be 0 unless you've done any rounding at all. And of course it is 0, so that means so far we're doing our math correctly. That's a nice way to kind of check that out. But now, once we've checked our math, we need to now go back and square all of these values. So if we square each value, 0.6 squared, negative 0.6 squared is 0.36. Again, it's positive. You always get a positive value when you square a negative value. Same thing over here. Anyway, 4.4 squared is 19.36. 18.4 squared is 338, blah, blah, blah. So I've squared all of those values. Now what I can do is add straight across because they have the same denominator. If they don't have the same denominator, you can divide first, then add. That doesn't hurt anything. So all I'm going to do here is add across, and what I get is 617.2. Now I can divide it by that common denominator, 26.6. That, of course, gives me a value of 23.2. So in other words, my chi-squared value is 23.2. Now, of course, at this point, to find out if this is a statistically significant chi-squared value, we first have to know the degrees of freedom that we have. We figure out the degrees of freedom for a one variable chi-squared the same always. So we do it just like we did in the two-cell chi-squared. We simply take the number of cells that we have in our table, our observed frequencies table, and subtract 1 from it. Because we had 5 cells in this case, of course, we have 4 degrees of freedom because 5 minus 1 is 4. It's different for two variable chi-squares, so please don't get those mixed up. I'll cover that in future videos. Okay, so now that we know we have 4 degrees of freedom for this chi-squared analysis, we look up our critical value in Appendix E of my textbook. If you don't have my textbook, you can just Google chi-squared significant values or chi-squared critical values, and you'll find several tables about this, and they should all be the same values. So here's a replica of what Appendix E looks like in my textbook, something like this, of course. All right, now we're looking specifically at the 0.05 level of significance, because we, of course, want to start with that. That is sort of the minimum level of significance, although maybe maximum level of significance that would be acceptable. How about that? That's a nice way of phrasing that. So we start looking at just that left row of 0.05 level of significance. That gives us a relatively low threshold for statistical significance. And I said that we have 4 degrees of freedom, and so we're looking just in the row that indicates 4 degrees of freedom. Where those two intersect, of course, gives us a value of 9.49. Okay, so our critical value, in other words, the minimum chi-squared value I would call statistically significant with this test characteristics, meaning 4 degrees of freedom, is 9.49. Because our chi-squared value that we obtained was 23.2, that is bigger than 9.49. Therefore, we have a statistically significant chi-squared value. Now, you may also notice it's also bigger than the 0.01 level of significance. So we also have a chi-squared value that is statistically significant at the 0.01 level. In other words, that's just saying we would expect to find a chi-squared value like this if there was no real pattern to the data only 1% of the time, or less actually, less than 1% of the time. Okay, so we do have a statistically significant chi-squared value. We can now reject our null hypothesis. Now, what can we do with this information? What do we tell Franz? What can Franz do? Well, this is interesting. On the one hand, we can go back and look at where was the biggest discrepancy that we actually saw. And as we can see, the biggest discrepancy, we're looking at that top, this is essentially the squared discrepancy score. In fact, that's exactly what it is, discrepancy between what we saw and what we expected to see. And as we can see, Franz saw way more number 3 hot dogs sold than he expected. And I can say that because I saw that this was a, first of all, it was a positive number before I squared it, a positive difference before I squared it, meaning that there were more observed than there were expected. And so he really outsold himself, his expectations, with hot dog 3. So what does he do? In fact, you can look down at the table as well to see that. See, he sold 45 of hot dog 3 when he really expected only 26.6 if the null hypothesis were true. So that means hot dog number 3 is doing really well. So a couple of things you might recommend. Maybe he should do more like that hot dog, or maybe he could try even improving on that hot dog and make it a different option. Maybe he should move it to his first menu item, because if that's the most popular item, maybe that makes sense. You could also look at these underperforming ones, because as you could see, the next biggest discrepancy was hot dog 4, 184, and it was a negative value because he sold fewer than he expected to. All right, so you might say to Franz, I don't know, maybe you should consider excluding hot dog number 4 from your menu entirely, and maybe adding a variation of hot dog number 3 or something like that. The point is that Franz can now use this information to make some intelligent decisions about his business and sell more hot dogs. Okay, that's it for this 5-cell chi-squared analysis. Next, we're going to do a chi-squared analysis that is still one variable, but we actually start off with the default position that we have different probabilities that we expect to occur. So I'll see you then.